This video is about constructing confidence intervals and conducting hypothesis tests for two independent samples proportions. So the proportions we're dealing with are coming from independent samples. Now first, confidence intervals. So these confidence intervals follow the same general form of any other that we deal with in this class. So that's PE plus or minus CV times standard error. And because we're dealing with proportions, this CV is going to be a Z alpha over 2, and this is going to be a left tail probability. So when we do alpha over 2, this is going to give us a negative Z-score. Now, when we're estimating two proportions, we're usually interested in estimating the difference of proportions, so P1 minus P2 is the parameter of interest. And so our best guess, or our point estimate for this parameter of interest, is going to be P1 hat minus P2 hat. Because P1 hat is our best guess for P1, that true population proportion for group 1, and P2 hat is similarly our best guess or our point estimate for that true proportion in group 2. And finally, we need an SE. The standard error of P1 hat minus P2 hat would theoretically be the square root of P1, 1 minus P1 over N1 plus P2, 1 minus P2 over N2. And that would be if we knew those true proportions. So if P1 and P2 were actually known. Now, because we're trying to estimate P1 and P2 are typically unknown. So when doing a confidence interval, or interval estimation, we use P1 hat and P2 hat to find the standard error. Now let's do an example. This is the example from the notes that was not worked out. So aspirin and heart attacks in Sweden. A Swedish study had 1,360 patients who had suffered stroke. The patients were randomly assigned to one of two groups, a placebo group with 684 people and 676 assigned to an aspirin regimen. After 3 years, the number of deaths due to heart attack in each of the groups were counted. The placebo group had a P1 hat of 0.041 and the aspirin group had a P2 hat of 0.027. And we can see that we have the respective successes or the counts of heart attack death rates in each of those groups provided as well. So we want to find a 95% confidence interval for the difference in death rate due to heart attack for the two treatments. So we're interested in estimating P1 minus P2. These are independent groups. No one who took aspirin also was given the placebo, and vice versa. No one who took the placebo was also given aspirin. So this is independent samples. So the point estimate, critical value, and standard error that we identified above work. So our point estimate is going to be P1 hat minus P2 hat, and they were kind enough to provide these for us, so we don't have to do that math. So it's going to be 0.041 minus 0.027, and that equals 0.014. Now, for the critical value, because again we're estimating proportions, we need at least 10 successes and at least 10 failures in each sample. Now we have 28 successes in sample 1, and with 684 people in sample 1, we can be sure that we have more than 10 failures as well. We also have 18 successes in sample 2, and with 676 people in sample 2, we can be sure that we have more than 10 failures in sample 2. So we've satisfied the sample size requirement, the success failure requirement in each group to be able to use the standard normal distribution, so we can get our Z-score. So we need Z alpha over 2 for our critical value. And we want a 95% confidence interval, so alpha is going to be 0.05, which is 1 minus 0.95. So alpha over 2, well, this is going to be familiar. This is 0.025, so we need a Z of 0.025, and we get this from the table. So as a reminder, just to practice this again, we're going to look for a z-score that has 0.025 probability less than it. So we look for 0.025 probability in the table, and we work our way out to the z-score. And we see that z of 0.025 is negative 1.96. So z with 0.025 probability less than it is negative 1.96. So all that remains is our standard error. And this is a standard error of p1 hat minus p2 hat. And remember, because we don't know that true proportion in either group 1 or group 2, we're using p1 hat and p2 hat to estimate the standard error. So this is going to be the square root of p1 hat, 1 minus p1 hat over n1, plus p2 hat, 1 minus p2 hat over n2. And when we plug in the p1 hat and the p2 hat that we had from our problem provided, we're going to have 0.041 times 1 minus 0.041 divided by 684. So this is the contribution to that variability from group 1, but we also have variability due to group 2. So that's going to be 0.027 times 1 minus 0.027 divided by 676. And working all this out, we get 0.00982. So we can see that because we have a very small proportion in each sample, and because our sample sizes are so large, we have a very small standard error. So now we just need to put these three pieces together, the PE, the SE, and the CV. So we're going to do P1 hat minus P2 hat plus or minus Z of 0.025 times that square root of P1 hat, 1 minus P1 hat over N1 plus P2 hat, 1 minus P2 hat over N2. And then we plug in. So we're going to have that point estimate of 0.014 plus or minus negative 1.96 for our CV times 0.00982. And our confidence interval is finally negative 0.005 up to positive 0.033. So, because our interval contains 0, that is, because our interval contains some negative and some positive values for the difference, we are 95% confident, or with 95% confidence, 0 is a plausible value. That means it is plausible that this true difference is 0. It is plausible that there is no difference in the 3-year heart attack death rate for aspirin and placebo groups. So using that same data, let's conduct a hypothesis test for that difference in proportions. Our hypothesis would be that there is no difference between P1 and P2, or that aspirin and placebo yield the same heart attack death rate after 3 years. Our alternative hypothesis, well, that would be that there is some difference in that heart attack death rate after 3 years. And so in order to make this meaningful, we have to define our parameters. So where P1 and P2 are the 3-year heart attack death rate for placebo and aspirin takers, respectively. And that's all you have to do. Now, the name of this test is a 2-sample z-test for proportions. It's a z-test for the same reason that we were able to use the z-critical value in the confidence interval. As for the assumptions required for this test, there are 3 of them. First, we need a categorical response. Now, because we have 2 samples, we had to have a categorical predictor variable to begin with, and that categorical predictor was the type of drug the patients were taking. And so the type of drug was either aspirin or placebo. And so that was categorical, so that was our categorical predictor. So now the response is also categorical, so that is survived or died. We also need independent and random samples. The independence allows us to use the standard error that we calculated above, and the random samples, well, that allows us to have an unbiased estimate for those true parameters we're trying to capture. And finally, we have to have at least 10 successes and 10 failures in each sample. And we already checked that, so we've satisfied all three of these conditions, so we are good to go. The next step in any hypothesis test is mechanics, and here we're going to assume our significance level alpha equals 0.05. 1, because this is our default, and 2, this is also consistent with a 95% confidence interval that we just did. The next step is to state a rejection rule, and we're going to reject the null hypothesis that the two proportions are equal if our p-value that we find is less than the significance level. So if we get a p-value less than 0.05, we're going to reject that null hypothesis. Now for the fun stuff. We have to calculate our test statistic. Because this is a z-test, we're going to have a z-test statistic. And this is a statistic. This is a z-obs. So again, this means this is coming from sample data. So our test statistic is going to be in the form of PE minus hypothesized value divided by the standard error of our PE. So this is the same form of any z-score we've ever seen. So in this case, our point estimate is P1 hat minus P2 hat. And our hypothesized value, well, we're hypothesizing that the difference is 0. And so even though subtracting off 0 doesn't get us anywhere, I put that in there just to emphasize that that is what we are subtracting. And then we're dividing by that square root of, wow, our standard error. Let's step aside for a second. If the null hypothesis is true, then P1 really does equal P2, and then the standard error would be the square root of P1, 1 minus P1 over N1, plus P2, 1 minus P2 over N2. And if that's the case, that P1 equals P2, well, then this would just be P, 1 minus P over N1, plus P, 1 minus P over N2, because these are all the same, if the null is true. And so if the null hypothesis is true, and we always do a hypothesis test with that assumption, we should come up with an estimate for our standard error based on this assumption. So we need to estimate this true P. So we use P hat, which is x1 plus x2 over n1 plus n2, to estimate the common proportion if the null is true. So where does that p hat come from? Let's start a new page. So our best guess for that common p is p hat is x1 plus x2 over n1 plus n2 equal 28 plus 18 over 684 plus 676 equals 0.0338. So we use p hat, 1 minus p hat, times 1 over n1 plus 1 over n2 for our standard error. So let's bring all this down onto that next page. Our test statistic then equals z obs equals p1 hat minus p2 hat minus the hypothesized value of 0 divided by the square root of p hat 1 minus p hat 1 over n1 plus 1 over n2. So that's going to be 0.041 minus 0.027 minus our hypothesized value of 0 divided by the square root of 0.0338 times 1 minus 0.0338 times 1 over 684 plus 1 over 676. When this is worked out, we get a z-score of 1.46. Our p-value, well, that's because, remember, our alternative hypothesis with p1 minus p2 is not equal to 0, so this is a two-tailed test. Our p-value is going to be 2 times the probability we get a z less than a negative z obs. So we're looking for a small tail to double that. So it's going to be 2 times the probability we get a z random variable less than negative 1.46. And we find that by going to the table. So remember, our z was negative 1.46, or at least that's the one we're interested in finding our p-value. So we have negative 1.4 here, and that 0.06 in our hundredths place, so we come down, we come across, and we get a left tail for our p-value of 0.0721. So our p-value is 2 times 0.0721, or 0.1442. So now we can write our conclusion. We fail to reject the null hypothesis because the p-value equals 0.1442, which is greater than alpha equals 0.05. We have insufficient sample evidence to indicate there is a difference in the 3-year heart attack mortality rate for aspirin and placebo. If we're interested in using that web app for comparing two groups, we can do this as well. So here we have trials and successes or binary observations. We fortunately have the summary information, so we don't have to enter over 1,200 individual observations. So for group 1, remember that was a placebo group, we had 684 observations with 28 successes. In group 2, we had 676 observations and only 18 successes. And the question was, counting for sample size, so comparing proportions, do we have a roughly equivalent number of successes between the two groups? So first we're going to do a confidence interval. So the confidence interval box is highlighted, and we're doing it at the 95% level. So we see absolutely we have a higher proportion of successes in group 1 and group 2, but is it higher enough to say that the placebo does nothing? So we've got our point estimate, our standard error, so these are the same values that we found before, plus or minus some rounding, and we have our confidence interval. We have our lower bound of negative 0.0049, and we had negative 0.005, and our upper bound of 0.033. And we can see that because of our giant sample size and because of our relatively small point estimates of 0.041 and 0.027, we have a very narrow confidence interval. So even though we have 95% confidence, our confidence interval itself covers only a tiny range of the number line. So let's conduct a hypothesis test or a significance test. So just changing the direction we look in, we want to know, well, is it plausible that 0 is the true difference? And so without changing anything else, we see that, well, for an alpha of 0.05, we're going to fail to reject the null hypothesis because we get a p-value of 0.144, which is much higher than that significance level. This is the same result that we got before.